unlocked.
Hi everyone, this is Marco, and this looks like a simple Pulley problem, but it actually hides three key questions: the tension, friction, and acceleration. Let's solve it step by step and see exactly when the system stays at rest and when it starts moving. So the problem is the following. A block of mass m1, 12 kilograms, rests on a rough horizontal surface. It is connected by a light and inextensible rope passing over a massless, frictionless pulley to a hanging block of mass m2, 7 kilograms. We want to answer three questions. The first question is, assuming the system is in equilibrium, find the tension in the rope, the static friction force, and the minimum coefficient of static friction. The question number two is, determine what happens if the coefficient of static friction μs is 0.5. And the question number three is, if the coefficient of kinetic friction μk is 0.3, find the tension in the rope and the acceleration of the system once it starts moving. So let's start with the step-by-step solution. In step number one, identify all the forces. So M1, the block with mass M1, is on a rough horizontal surface. So the friction acts on it, and we can call the friction coefficient as μs. The second block instead hangs vertically, so its weight pulls downward, and we may call its weight W2. W2 equals m2g, and the vector points downward, as you can see. So, if the system is initially in equilibrium, the static friction force Fs on m1 must act to the left, opposing the tendency. So, if m2 pulls downward, the friction must act toward the left direction, okay? So that the system stays in equilibrium. Okay. Now, let's start first with examining M1 only. That's how we solve this problem. First, we examine the block number 1 and then the block number 2. And we see what are all the forces acting on each block, okay, separately. So, first examine M1 only. And in doing that, we need to have a proper coordinate axis so that we can write the vectors. And we may say that the tension of the rope is directed towards the right, so along the positive x, while the static friction is towards the left, so along the negative x. The weight acting on the block 1, so on the mass m1, is going downward, okay, so along the negative y. So we can call it w1 equals m1g, okay, and they are both vector, the force, the weight, and the acceleration g, of course. And then we need to consider also the normal reaction force n, which goes upward along the positive y, okay? So now examine the block number 2, examine M2 only. And the x-axis follows the direction of the rope. So in this case, you may see that the x-axis is going downward because the rope is now going downward, okay? Very good. So previously with the block number 1, the x-axis was horizontal, following the rope. But then after the pulley, the rope is going downward, so the x-axis is going downward as well. So the weight is acting on the block number 2, and the weight is W2 equals M2G, is a vector pointing downward, okay, so along the positive x. And the tension, we call the tension T2. The tension in the rope is going upward, so along the negative x, okay? Now let's go to step number 2. Considering the system that is initially in equilibrium, we solve for M2. There are only two forces acting on M2, as we have already seen. The system is in equilibrium, the block is at rest, so the net force must be 0. And then we can write that the sum of all the forces along the x-axis must be equal to 0. But we know already what are those two forces, is m2g positive minus t2, because it's negative, is going upward, equals 0. And then we can have that t2, if we make some calculations, turns out to be 68.6 newtons. Okay? It's a very easy calculation. Now, since the rope has negligible mass and is inextensible, that's very important, the tension T in the rope must be the same at any point of the rope. Okay? That's an approximation, of course, we are doing. And thanks to this, we may assume that the tension in the rope is the same in any point of the rope. And therefore, we may write that T1 is equal to T2, it's equal to T, we can call the tension T along all the rope, and then it's equal to 68.6 newtons. So we answer the first question in number 1. So the question number 1 has 3 parts. We answer the first part of the question number 1, solving the equation for the block M2. In the next step, which will be step number 3, we solve the equations for the block number 1, so for M1, okay? Again, the system is initially in equilibrium, so we need to consider that the block M1 is at rest, so the net force must be 0 along both axes, so the sum of all the forces along the x-axis must be equal to 0, and the same, all the forces along the y-axis is equal to 0. Okay, so we have two equations, and so along the x-axis we may write this as t. I remember that t1 is now t, because t1 is equal to t2 and it's equal to t. So t minus fs equals 0, and that's the first equation along the x-axis. And then with this we may calculate the friction, the static friction, which is the same as the tension, 68.6 newtons. And then with this we answer the second part of the question number 1 on the friction force. Solving instead of the y-axis, we may write down that the normal force N must be equal to m1g, so to the weight W1, all right? And this is equal to 117.6 newtons. So with this, we basically calculated the normal force. And we know that the static friction adjusts to the applied force, meaning that it's not a stable, a steady force. It doesn't have a determinate value, okay? The static friction changes depending on the force applied on the block until the block starts moving. But as long as the block doesn't move, the static friction changes depending on the applied force. So it adjusts to the applied force up to a maximum value mu s n. And when the force, the applied force, is greater than mu s n, then the block starts moving, okay? So the static force Fs is less or equal to mu s n. This is the first relationship, or we may write also that mu s n must be greater or equal to Fs. So the minimum value for mu s, we may call it mu s min, to keep the system at rest, is then mu s min equals the static force over the normal force, and this is equal to about 0.58. So with this, we answered completely question number 1. So all the 3 questions inside question number 1 now are completely answered. So let's go ahead with the step number 4 now, and let's answer the question number 2. What happens if mu s equals 0.5? Now, since mu s it's less than mu s min, which is equal to 0.58, because mu s is 0.5, which is less than 0.58, we then expect the system to start moving. In fact, the maximum static friction Fs max is now We make a calculation, okay, and it turns out to be 58.8 newtons, which is less than 68.6 newtons, which is equal to the tension. So it means that the maximum static friction force is less than the tension. So the tension starts pulling the block number 1, and the block number 1 starts moving to the right. Okay? And what will happen to the hanging block? The hanging block, of course, will move downward. So the block on the table will move to the right, and the hanging block will move downward, of course. And let's remember always that T1 is equal to T2 and is equal to T, so the tension in the rope is the same. Let's go ahead with step number 5 and move to the question number 3. We use the Newton's second law and kinetic friction. So why kinetic friction? Because the system is moving now. So we are not going to use the static friction force. We're going to use the kinetic friction force and the coefficient of kinetic friction, because the system is moving. So once the system starts moving, the static friction is no longer acting, and we must use the kinetic friction instead. And the kinetic friction is given by Fk equals mu kn this time. Okay, so we substitute Fs with Fk, we substitute mu s with mu k, and the relationship is the same. So we have that Fk equals roughly 35.3 newtons, okay, after some simple calculations. Okay, now for the block M1 on the table, the motion is of course to the right, because the tension is pulling the block to the right. Applying the Newton's second law, we know that the sum of all the forces equals M1 in this case times the acceleration. And we need to apply the Newton's second law along the x-axis. Okay? So we need to have all the forces acting along the x-axis, and we have the tension T, which acts to the right, and so will be positive, and the kinetic friction Fk acting to the left, so it will be negative. Okay? In this case, considering the x-axis, we may write down that T, positive, minus Fk equals M1 times A, and this implies that T minus 35.3 Newton, which is Fk, equals 12 kilograms, which is the mass of the block number 1, times the acceleration. And we have the first equation in this case. Now there is a note. So we assume that the sign of the acceleration is positive, so we expect a positive value. So we assume that the acceleration is going to the right. So we assume that the system the block number 1 is moving to the right. So we expect the acceleration going in that direction, okay, going to the right. And therefore we expect a positive value for the acceleration. We expect a positive value, but in general, if we have any doubt or we don't know in which direction the acceleration will be, because we have maybe a more complicated system, maybe with 3 bodies or in a different configuration, so we are not sure in which direction the acceleration will be, we decide for a positive direction for the acceleration, we make all the calculations, and then in the end, if the numerical value is negative, this will imply that the system will move toward the negative side of the axis we have chosen. So in this case, we chose the positive side of the x-axis going to the right. So we expect that the sign of the acceleration will be positive if the system moves to the right, if the block number 1 moves to the right. But if, for instance, not in this case of course, but if the block number 1 would move to the left, then we are going to have a negative value for the acceleration. If we have a negative value, it means that the acceleration is going in the opposite direction of the positive value of the axis we have chosen. That's the key point here. So we have now two unknowns, the tension and the acceleration, in one equation only. As you can see, we have the two unknowns, t and a, in the blue squares, and in the green rectangle we have our one only equation so far. So we need to find the second equation, and to do that we go to step number 6. So let's go ahead with step number 6. We write down the Newton's second law for M2 in this case. The M2 is the hanging block, so the motion we expect to be downward. And applying the Newton's second law, we have that the sum of all the forces must be equal to m2 times the acceleration. In this case, along the downward x-axis, okay? Because the x-axis has moved from being horizontal to vertical because of the pulley, because the rope changed direction, as I said before. So we have now two forces acting along the x-axis. The weight W2 acts downward, so in the positive direction, and the tension T acts actually upward, so in the negative direction. So we have M2G, so W2, the weight, M2G positive, minus the tension equals M2A. And this implies that we have this equation, 68.6 Newton minus the tension equals 7 kilograms times the acceleration. And this is the second equation we have, but that we need to couple with the first equation. We need to note an important fact here. The acceleration A is the same for the two blocks because the rope is assumed to be inextensible. So if the rope do not extend, of course the acceleration of the block number 1 must be the same of the acceleration of the block number 2. That's why usually in the text of the problems, the rope is assumed to be inextensible and massless, and also the pulley is massless, because makes the problem, of course, easier than it would be in case the rope had a mass or the pulley has a mass. This will be done in other problems. For now, we stick with the simpler problems. So let's go ahead with these assumptions that the rope is assumed to be inextensible, and therefore what we have is that the acceleration is the same for the two blocks. We have now, since the acceleration of the block number 1 is the same as the acceleration of the block number 2, we have now two equations, the one we found in the step number 5 and the one we found now in step number 6. We have two equations with two unknowns, t and a. So we can solve those two equations, and we are going to do that in the step number 7. So in step number 7, we solve the system of the two equations. We are written here. Now, if we add them together, we note that t is eliminated, and therefore we have that basically 33.3 newtons equals 19 kilograms times a. So the acceleration is 1.75 meter per second squared. That's the first answer we have, so the first unknown. And then if we use again the first equation of the system, so t minus 35.3 newtons equals 12 kilograms times a, but we know the value of a, so we can solve for t, and we find out that t is equal to 56.3 newtons. Now, we answered also completely question number 3, and we note that the acceleration a is positive. Therefore, the system, as expected, moves along the positive x-axis. So the problem is totally solved, and I want to remind you that this problem has been solved with the SILU method. Thank you very much. Subscribe to the channel if you find it useful, and please don't forget to like as well. Thank you very much. Bye bye to the next one.
Physics Unlocked.